Alright everybody, let's talk about question 4 here, which is talking about obviously a volume and an area question. If you notice here, the region R that they told you was bounded by this square root function as well as this x divided by 2, and you're asked to find the area of the function. Okay, and so obviously the area would be the I would definitely go vertical strips here, but you could do horizontal strips if you wanted to. So vertical strips would be taking the integrand from 0 to 4 of your upper minus your lower, so you'd have square root of x minus x over 2. And then you do in fact have to go through and do this by hand, so you would have x to the 3 halves divided by 3 halves, which would be multiplying by 2/3 minus x squared over 4, and then you put your 4 in and your 0 in here, and you do in fact get 4/3. Let's really kind of talk about this x to the 3 halves. When I put 4 in, 2/3 times 4 to the 3 halves, I always cube that and then put it back under the square root. And so two of them will pop out of 4, so that would be 2/3 times, so that'd be 4 times, and then I still had a 4 left inside, and the square root of that inside piece would just be 2. And so you'd have 8 times 2/3, so that would be 16/3 here, minus, and then when you put 0 in, you obviously get 0. Oh, I'm sorry, I forgot to put my 4 in here, so that would be 4 squared is 16 divided by 4 is 4, so that would be minus 4 here, and then minus 0 here. So when I get thirds here, that would make this a 12. It's really sloppy, but 16 minus 12 is 4/3. And so you get your answer at that point. You can totally leave it like this and not, you could just leave it as 16/3 minus 4, and that would suffice. You get your point for the correct integrand, this piece right here. You get a point for the correct antiderivative, and then you get a point for the answer, which could be this or 4/3, either way. Part B says to find the volume of the solid that's formed when you take squares and put them in here. So our squares are perpendicular to the x-axis, so they're going to be vertical strips. If you can see this kind of popping up out, there's my square, and the area of a square is base squared. So when I integrate this, I will go from 0 to 4 of my base. Now your base is your upper minus your lower, and your area formula will be to take that and square it. So I have the integral from 0 to 4 of this nasty thing squared, and I'm really, really sorry, but yes, you are going to have to FOIL that out to get the antiderivative using the power rule. So FOIL out that square root of x minus x over 2. You'll get this when you clean it up, and now you find your antiderivative. So your antiderivative of x is x squared over 2 minus x to the 3 halves. You add a power, 5 halves, divide by that power, or multiply by the reciprocal there, so that's how I got my 2 and my 5. And then x to the third divided by that third, but there's already 4, so that's how we get the 12 there, okay? Now, when you are putting your 4 in, it gets really, really, really gross. So you would have 4 squared over 2 minus 2/5 times 4 to the 5 halves plus 4 to the third over 12 minus, and then everything you get when you put zeros in will just give you zeros. And so again, folks, if you are in a time crunch, leave it here. This is totally okay. You are allowed to leave it like that. And in fact, I would advise you to leave it like that, because if you continue and you happen to make a mistake, they will count your mistake as an error, and you will not get the answer point. But this right here will give you the answer point. Isn't that wonderful? And then the last part, part C, says write it but do not evaluate an integral expression for the volume of the solid that's generated when r is rotated around this line, y equals 2. Okay, so if you want to kind of visualize this, we have this line going through here, and this guy is coming down here like so, and we're revolving it so you can see that I have here kind of a funnel looking thing, but it's not going to have a hole in the very bottom of it down here. And then you have slices of bread being donuts, basically. And so when you set that up over here, you're going to have the integral from 0 to 4 of pi times something squared minus another pi times something squared, because you got to subtract that out, with respect to x. Now I'm going to go with respect to x, obviously, because I have a horizontal line of axis here, axis of symmetry. Now let's just talk about how to get this first piece. That distance, I know that from here to here is 2. So when I go from here to here, I've got to subtract out the value of that lower function. And so that's why I have 2 minus the lower function being x over 2. And then in this case it will be 2 minus the upper function, which would be the square root of x. And that is how they got their answer. You could leave it the way we had it up here, where you have your pi's in. You could factor your pi's out if you'd like to do that. Please do not do this. Pi times the integral from 0 to 4 of 2 minus x squared minus 2 minus the square root of x all squared. That is a no-no. This square cannot factor out. Please don't make that mistake. Leave it alone, okay? You can see you get your point here for having the correct limits and the correct constant. I think that would be pi hanging out there. And then you get a point for the correct integrand. But again, this expression right here will award all of the points to as well. All right, let's talk about question 6, which is this question that deals with motion along a line. And they give you some values for time and velocity, okay? So the part A is saying estimate the acceleration of the particle at 36 seconds. Obviously you don't have a 36, that will always usually happen. And so you want to find the derivative using the 32 and the 40 timestamps. So your acceleration at 36 would be your velocity's derivative at 36. So you want to set this up and have v of 40 minus v of 32 all over 40 minus 32. And when you actually do take those values and subtract them, you'll get 11/8 meters per second squared. Notice they're going to give you a point for having the correct units in A and B. So if you got the correct labels for A and B, you get 1 point overall for the whole entire question. Here you get a point just having your 11/8 meters per second squared. Part B says, using correct units, explain the meaning of the integral from 20 to 40 of your velocity function in terms of time in the context of this problem, and then use a trapezoidal sum with 3 subintervals indicated by the data in the table to approximate that value. So you are integrating your velocity, so that should obviously give you the change in the position in meters from times 20 to 40 seconds. Don't forget to put that timestamp there. And then you will evaluate that using trapezoids. Please don't make the mistake that you're going from 0 to 40. You'll have a really hard time splitting that up into 3 sections with the data they gave you. So use the data they gave you here with 20 to 40. So again, your widths are not the same. This is a width of 5, this is a width of 7, and this is a width of 8. And so you have to set these up separately, and that's something that we're seeing a trend on the AP test, where you really just have to know your trapezoid rule, b1 plus b2 over 2 times your width, or your height rather. So v of 20 plus v of 25 over 2, v of times 5, and so on and so forth. When you work that out, you will get negative 75, and that would be meters because it's a position value, okay? So you get a point for having the correct meaning. That's this up here, saying that it's the change in the position over 20 to 40 seconds. And then a point for having negative 75 as the answer out there, okay? And part C, it says over 0 to 40, must the particles change in direction in any of the subintervals indicated by the or do we know it changes direction if we do know, explain when that happens. And you know that velocity is zero, or rather velocity changes from positive to negative or vice versa at those points where it changes direction. And so we can see that from 8 to 20, it's going to have to equal 0 somewhere, and from 32 to 40, it's going to have to equal 0 somewhere in there. So therefore, the particle changes direction in the intervals from 8 to 20 and 32 to 40. You get a point here for having the answer listed out correctly, and a point also for your explanation in that case. Okay. And then lastly, I wanted to take a moment and just kind of make sure we're all on the same page about part D. It says, suppose that the acceleration is positive over 0 to 8 seconds. So basically, you know that the slopes of the velocity are positive over those 8 seconds. Explain why the position of the particle has to be greater than 30. Okay? Now, when I was going through and thinking about this question, I kind of just drew out here this velocity data. I know that at time 0, it was 3 units. And at time 8, this is coming from the data in the table, which I don't have it on there, it was 5 units. And I know that it was always increasing over that. So if I'm talking about position, I'm talking about the area under the curve in here. Okay? Well, I know if I estimated this on the low end, which is using an LRAM, that this distance here, this width of this rectangle is 8, and the height of this rectangle is 3, and 8 times 3 is 24. And I also know that at time 0, his position was 7 meters, so 24 plus 7 would equal 31. So on the low end, I know that my area, that my position has to be at least a 31. So if you go through and explain that in words, succinctly and concisely, what they have here kind of isn't something I would assume you'd be thinking of to write. I would just say that if I use an LRAM, a left Riemann sum, to approximate the area, the least it could be would be a 31. So it has to be greater than 30. Okay? So recognizing that your acceleration is the derivative of your velocity because of the slopes, and then your explanation of how it has to be greater than 30 would receive you 2 points there.